In this assignment, we're going to look a little bit closer at functions, their graphs, and properties of functions. In this problem, they're asking us to identify the equation that goes along with that graph. Now that's a parabola. The standard form of the equation for a parabola looks like this. And from that equation, if we were to graph that, we would have a parabola whose vertex would be at the origin, or 0, 0. So looking at the graph they gave us, we can see that this point, which was 0, 0, has moved over 1 to the left, or 1 to the right, and up 3. So how would we show that from what we know about translations of graphs in previous lessons? How would we show that in a parabola with that equation? Well, what we could do is this. We could say, well, let's see, we've shifted the x 1 to the right. If you remember, we subtract 1 from x in order to shift it to the right 1. So we could say, in this case now, substituting f of x for y, we can say we've got x minus 1, that shifted it to the right, but remember you square it because that's the shape of the graph. And then we wanted to move it up 3, so outside of the original function we would add 3. So that'll move it 1 to the right and up 3. So which one of those answers up above fits this or matches this? It looks like C. C matches that. So that's based on translation. And what we're going to find is what we learned in translations earlier applies to other shapes and other graphs. So that's what that problem is trying to show there. Now looking at this graph, in the following exercise it says find the coordinates of the vertex for the parabola defined in the given quadratic function. So this is kind of going backwards from what we just saw. Remember that the basic function has to do with x squared. What have we done to the x? Well, we've moved it 2, but this time we've moved it 2 to the left. And we've moved the whole function up 5, and the vertex used to be 0, 0. So if the function started at 0, 0, and we've gone 2 to the left, our x value is now minus 2, and our y value has gone up 5, so from 0 it's gone up to 5. So that would be the vertex now, negative 2, 5. Let's see. What can we learn from looking at a parabola? Well, we actually can use parabolas to find some very useful information. For instance, Farmer Ed has 500 meters of fencing and wants to enclose a rectangular plot that borders on a river. And here's the picture of it over here. If Farmer Ed does not fence the side along the river, find the length and width of the plot that will maximize the area. What is the largest area that can be enclosed? Well, first of all, we have to go back to something we learned many years ago, and that is the equation for the area of a rectangle. The area of a rectangle is length times width. And looking at the drawing, they've actually given us the length and the width. They've said, let's make the width x. But I'm using fencing on both ends of that field, so I have x on the left-hand end and x on the right-hand end, so that's 2x of fencing. I started with 500, so the long side has got to be what's left after I've done the two short sides. So that's the 500 originally minus those two x's. So now I have an expression for the length and an expression for the width. So the area is going to be the length, which is the 500 minus 2x, times the width, which is x. Watch what happens when I distribute the x. I get 500x minus 2x squared. Now, if we were to write that in a quadratic equation, we'd put the highest power first, so we would write it like this. Negative 2x squared plus 500x. This negative in front of the 2, which is the coefficient of x squared, tells us which way our parabola is going. A negative is going to be an upside down parabola. It's going to open downwards, and it's going to look like this. And since it looks like that, it has a highest point. Remember what we're trying to do is we're trying to find the maximum area. Remember, this is the equation for area, and it has a maximum value. Where is that maximum value? Well, the maximum value occurs at the vertex. And we have an equation for finding the values of the vertex of a parabola. The x value for that point is found by minus b over 2a. Now, what's the a, the b, and the c? We're not looking at the c, but it is there. So the standard form of the quadratic equation looks like this. ax squared plus bx plus c. So a is always the number in front of x squared, b is always the coefficient or number in front of x, and c is the constant term. In this case, we don't need the constant term, but we do need the number in front of x and the number in front of x squared. Well, we have that. The number in front of x is 500. So x is going to be minus 500 divided by 2 times, well, the number in front of the x squared is negative 2. So this is minus 500 divided by minus 4. That equals 125. So that's where it occurs. It occurs at when x is 125. Now that's the length of those two sides. Well, we need more than that, though. We need also the length times width in order to figure out what the area is. So if we were to take that first equation up there, 500 minus 2x times x, that would give us the area. Well, 2x, 2 times 125 is 250, and 500 minus 250, well, 250 is half of 500, so that leaves us another 250. So let's start over here. 500 minus 2 times, now we found out that x is 125, times 125. And that's going to be 500 minus 250 times 125, which is 250 times 125. Okay. And then I'll leave that up to you all to multiply that out on your calculator. But that is how you find now the area surrounded 3 sides by a fence when you're trying to maximize the area. That's how you should choose the size of that field. Okay. let's go on. Let's look at number 8. What this graph is showing is the heart rate of a person watching a short romantic film, where X represents time in minutes and Y represents heart rate in beats per minute. So I want to answer the following questions. For which time periods was the person's heart rate increasing? Well, on a graph, if you're increasing, you're going up. So we would say that we were increasing in this time area here and in this time area here. Well, the first time area is the time between 1 and 3, and the second one is between, it looks like 9 and 11, so that would be D. That was D. For which time periods was the person's heart rate decreasing? Well, now what we want to do is look at where we're going downhill. And looking at that graph, it appears that it's going from 3 to 11 and from, I'm sorry, 3 to 9 and from 11 to 15. So we would say 3 to 9 and from 11 to 15. How many turning points? Now this is important to understand. How many turning points are happening there? Well, if we look at the graph, this is a turning point right here. Start turning from going up to going down. So here's 1, there's 2, and there's 3. So where we're turning from going down to back up, from up to down. We would call all of those turning points. So we would say there are 3 turning points. So suppose the polynomial function is used to model that graph. What's the degree of the polynomial function? Wow. Well, I guess we need to know something about polynomial functions and their degrees. So let's leave this for a minute. And I'm going to bring up a blank page. And let's talk about the different shapes of functions. One of the functions we spent a lot of time on already is the linear function. Remember, that's the one where the equation looks like y equals mx plus b. But it's x to the first power, that's the key to it. And if m is positive, or the slope is positive, then our line goes uphill. If it's negative, it goes downhill. Now, the second kind we're looking at is what's called the parabola. Which is this, second power, and if it's positive, it opens upward, sometimes called the smiling face. If A is negative, it goes down, sometimes called the frowning face. Well, the third one would be what we would call x cubed. I'm not going to put the rest of it in there. There's a third power. It's shaped like this. Some people call that the snake. If it's negative, it goes like that. If we have the highest power is x to the fourth power, then it looks like this. And if it's negative, it looks like that. If it's the fifth power, it's going to look like this. And that. It's the sixth power. Now, how do I know that? Did I memorize all those shapes? The answer is no, I didn't. Let's take a look at something. There's some patterns here. Look at your odd power, the 1, the 3, and the 5. So the odd powers is the 1, the 3, and the 5. They all follow a particular shape of going uphill if they're positive and coming downhill if they're negative. They have a different number of humps in the middle, but what's happening on either end of the function, we call the end behavior, is the same for the odds. They go down to the left and up to the right if they're positive, or they go up to the left and down to the right if they're negative. Well, the even functions, even powers, 2, 4, 6, they all follow a similar pattern. Those are these. If they are positive, they form a U shape opening upwards. Notice the 4 does the same thing, it just has an extra hump in it. The 6 also is a U shape upwards with a couple extra humps in it. And if it's negative, it goes down. The two ends both go in the same direction, positive or negative. So now, knowing that, let's go back to the problem we were given. Which one of those functions best models what's happening there? Well, notice that the two ends are going down, so we know it's an even function. And it's not quite a parabola because it actually has an extra turn in the middle. So that is probably a 4th degree. That's what we would call that. So suppose that a polynomial function is used to model the data. What's the degree of the polynomial of best fit? It's always the highest degree in the polynomial. And we would say that that number is 4. So what should the leading coefficient be? Should it be negative or positive? Well, looking at that graph, the ends are going down. If you remember from the shape of the evens, they open downwards when the leading coefficient is negative. So we know that it's negative. Why is it negative? Because the graph rises to the left and falls to the right? No, it's falling in both directions. It's negative because the graph falls to the left and falls to the right. Now, what's the maximum heart rate during that whole episode? Well, it's the highest point on the graph. If we look at it, it's right up here. Looks like about 74. And after how many minutes did that occur? Well, the minutes are the x-axis, so that occurred after 3 minutes. What about the minimum heart rate? Well, you might want to say it's this point right here where it turns around. But if you notice at the very end down here, it actually goes even farther down. So the end point in this case is where the minimum occurs, and that's at 55. And it occurs at 15 minutes. Okay? That's how you do that problem. Let's go over to number 11. Here we're going to talk about something called the horizontal asymptote. So what is an asymptote? Well, an asymptote actually is something you can never get to. And it occurs for several reasons. For a horizontal asymptote, sometimes our functions are going to do things like this. They're going to tend to get closer and closer to something but never actually get there. They're going to flatten out. So this one looks like it gets closer and closer to the x-axis. We would say that the horizontal asymptote is y equals 0 because that's the x-axis is y equals 0. Well, let's see. How can we figure out what that horizontal asymptote is? Well, the tool we're going to use is that as this goes out farther and farther, it's getting closer and closer. So maybe what we ought to do is investigate what happens as x gets very, very big. In other words, as it goes way out the x-axis, what's the equation getting close to? Let's take a look at this. If I take this equation, and I start talking about what's going to happen as x gets very, very big. I mean very, very big, like a million or a billion or a trillion. Well, the top would be minus 6 trillion plus 5. Does that plus 5 really mean a whole lot anymore as x gets to a billion? Minus 6 billion plus 5. And the same thing on the bottom, 7x would be 7 billion. Plus 5. I don't think those 5s are very meaningful when x gets very, very big. So we can drop them and say we're approximately the same as, we use this symbol for approximately. It's not exactly equal, but it's very much approximately equal to minus 6x over 7x. Only though when x is very, very big. Now, what can I do? Oh, I can cancel those x's out. Because even if they're a billion over a billion is 1. So it still works that those can be canceled. So minus 6/7. And that turns out to be the horizontal asymptote. But while we're here, let's look at what could have happened here. What if instead of that equation, I'd had this equation? And the thing I've changed is I've squared this one. Now, the plus 5s, when x gets very, very big, the plus 5s really still cancel out, or don't mean anything. They don't cancel. They just don't mean anything. So this is still approximately minus 6x over 7x squared. Well, I can't cancel the x's like I did before, but I can cancel 1x with one of these x's. Remember, this is x times x, so that's x times x. One of these x's and one of those x's can cancel out, and what I end up with is I still have the other x is still there. Remember, this was x times x, only one of those x's canceled, so I still have an x left over. Now, let's examine what that's going to be. If I have x being very, very big, like a billion, that's minus 6 over 7 billion. Is that a big number or a small number? Well, when you have a very big denominator, you have a very small number. Let's think of some that are more identifiable. 1 over 10 is 1/10. 1 over 100 is 100th. 1 over 1,000 is 1,000th. 1,000th is very big, very small. 1 over 1,000,000 is 1,000,000th. See how that's getting smaller and smaller and smaller. So minus 6 over 7x as x gets very, very big, a billion, a trillion, etc. What are we getting close to? We're getting very, very small, so we're getting closer to 0. So the horizontal asymptote, although the graph never gets there, the horizontal asymptote is going to be like this one you're seeing up here. It's going to get closer, closer to 0. So, this is the horizontal asymptote here. Down here, the horizontal asymptote would equal 0. There's one other case, though. I could have had minus 6x squared plus 5 over 7x plus 5. So what I've done here is I've now put the higher exponent on top, the lower exponent on the bottom. Again, the plus 5 on top and bottom don't mean a whole lot when x gets very, very big. So this begins to approximate minus 6x squared over 7x, which one of the x's can cancel. I'll have minus 6x over 7. And what's going to happen as x gets very, very big? Well, now the numerator is getting very, very big over 7. So if I had a trillion sevenths or a billion sevenths, remember each 7 of those forms 1. So it's like taking a billion and divide by 7. It's still a big number, isn't it? And of course, as x gets bigger and bigger, that's only getting bigger and bigger also. So instead of approaching something, it's taking off like a rocket ship. It's going through the roof. So that one has no horizontal asymptote, because an asymptote is something you get closer and closer to but never get there. So we would say here, no horizontal asymptote. So let's review it. See if we can form some rules. If the highest power on the top and the highest power on the bottom are the same, then they will cancel out and we'll have a horizontal asymptote, but it's going to be equal to the original coefficients of that highest power, the minus 6 over 7. If the highest power is on the bottom, what's going to happen is, as we simplify this, we're going to end up with a denominator getting very, very big. And if a denominator is big, the fraction is small. So we're approximating, we're going to approach 0. If the power on the top is higher than the power on the bottom, then as we simplify it, we end up with a very high number on the top with a fixed number on the bottom. And the bigger this gets, the bigger the whole thing gets, which means we're not approaching anything, we're running away from everything. We're getting bigger and bigger and bigger, faster and faster. So there's no horizontal asymptote. Okay, so what is the case here? Well, they're the same, so the horizontal asymptote should be negative 6/7. Okay, let's go look at another. So let's use transformations now to look at a rational function. And in this rational function, we're going to define f of x as 1 over x squared and then ask what's going to happen to g of x. Well, we have to know, first of all, what does 1 over x squared look like? What does f of x look like? Well, of course, you can do this on your calculator to take a look at it. What it does is it is asymptotic to the x-axis and the y-axis. It comes back down and asymptotic to the x-axis again. And that's the function I drew for you in the last example. That's approximately what 1 over x squared looks like. Well, what does g then do to that? Well, notice the 6 on the right. That's added outside the fraction. So that's like it's outside the function. So that's going to move us up 6. The x is modified by subtracting 3 from it. If you subtract 3 from x, remember what you do. You move it to the